The last time what we had discussed was the precision recall. As we increase precision, the recall drops and vice versa, right? So what we learned earlier was, if let's say out of all the predictions on the test data, what we do is, instead of asking the system about the only predictions, if we ask about what is that probability, or what is that number that defines chances of something being predicted right. Okay, if that, let's say there is a system, such system whereby we have the individual priorities, or if we get the score on every value. I'll just go back to this place. So imagine that for everything we got the score. Okay, that when we are matching 5, what is the score, and so on. So if we increase the threshold for this score, that okay, in case the threshold is this much, something will be predicted as this, and so on, or the predictions will be like this. So if the threshold is midway here, the predictions on the right are the predictions with the score higher than the threshold, while the predictions at the left are the predictions with less score than the threshold. Okay, so they will not be predicted while this will be predicted. And or you can say confidence score, right? This is being predicted with certain confidence, this is being predicted with certain confidence, and this is the highest of all the other predictions for the image, right? So imagine that our algorithm is giving us the maximum prediction score for every digit. Okay, and what we do is we decide upon this threshold. Okay, let's say threshold is somewhere here, and as we increase or decrease this threshold, the predictions will vary, correct? So as we decrease or drop the threshold, more and more wrong predictions will be done, as well as right predictions will also increase. And some of the right predictions will increase. For example, if we drop it to this level, these predictions will also be correct. It will be like this, that out of total predictions, these many will be predicted, right? Now, so as you can see that as we are varying the threshold, the precision is increasing, because earlier the precision was somewhere here, and the recall was 100%. As we move the threshold to the right, what happens is the recall drops to 67% and precision increases to 80%, right? So further, as we move to the right, as we increase threshold, the recall will improve, recall will drop to 50, and precision will improve to 100%, right? So that's about the precision and the recall trade-off. Okay. Now we had talked about it that precision reduces recall and vice versa. So we had drawn this. So we had asked the classifier about the decision function. About the decision function, we got the scores of every digit. Then we were free to start the predictions. Okay. Okay. So here, these are the scores for some digit, and we got the scores, and then we checked about the threshold, and then we set the threshold to certain value, and then we check that. So this particular digit was false when threshold was high, and same one was prediction was true when the threshold was low. Okay, so so by selecting appropriate threshold, the user can obtain the desired position. However, the best precision may not have the best recall. Okay, so what we do in general is that we decide upon the threshold value based upon our requirement. Okay, so get the score of all the training sets using crossword predict. With this, compute the precision and recall for all possible threshold using precision recall curve. Plot both precision and recall for the threshold using matplot, and then select the value that gives the best precision recall trade-off at the end. right? So if you are solving a problem, let's say videos or kid safe videos, in that case, you would like to choose a high threshold, right? So that the precision is high and the recall is low. So this is something as data scientists you will have to figure out by talking to the people who are the product managers or the people who are interacting with the end user, or take a look at take a look at the user behavior, keep your numbers extremely clear. So you need to, at this point of time, to basically figure out what is the threshold value. You have to look at the problem at hand, right? So this part we had already done, and then we plotted this. So this is the point where the precision is also maximum, and recall is it. Basically, precision and recall are at the same value. Okay. So probably this is the point you would like to choose and so on. And then, so you can also plot the precision directly against the recall like this. So as precision is going down, the recall is improved, or as recall is going up, the precision is going down, right? So you can see that in the best case scenario, the precision could have never gone down, right? Even if the recall was going up. Okay, meaning as we are dropping the threshold, right, more and more recall is happening, right? Even then there should have been no wrong predictions. So in that case the precision would have been like 100%. Okay, so in the ideal scenario, what will happen what should have happened is this line should have been like this, meaning even if let's say, so when we have threshold very high, so if you have a little bit of confusion about, let's say, is it 5 or is it 4 in the drawing, you were basically dropping it, saying, hey, I don't want to take a risk, I will drop it here, right? That's what is happening. If you are instead of training a model, if we are telling our team to do it manually, so we'll tell that, hey, these are very highly sensitive things, you don't make a mistake. It's okay to let it go, no, but not okay to make mistakes, right? Then the recall will be really low, because they will say, okay, this looks a little bit confusing, may not be a perfect 5, so let's drop it. It's not 5, or it's not 4, it's not 3, right? And as you do that, here the precision would be would be good, right? Because you're not making much mistakes. Okay, as you say that, okay, it's important to take a decision whether it's wrong or right, but take a decision. Okay, so as you do that, um, the precision will start dropping, but being able to take decision or being able to recall will be higher, right? In the perfect, the smartest cases, like like the people who are snipers, in those cases, the even if they have a higher recall rate, even if they, let's say, if there's some team members, if they, even if the something is drawn really bad and the score looks bad, even when their precision does not drop, meaning they don't confuse the letter with something else, right? They don't say that, oh, it's not 3, it's 5, it's not 5, it's 4, right? So they don't have that. So in that case, the precision will be like straight. Okay, so I hope everybody got the idea about precision and recall curve. All right. So similar to the precision recall curve, the one that we discussed, right? There's something called ROC curve. So what we do is we draw similar to exactly like this. We leave the recall on one axis, and on this, on y-axis, what we draw is instead of precision, we draw the true positive rate. Sorry, we draw the false positive rate. or you can say true negative rate. And so basically, it's exactly like this. What we do is we draw true positive rate versus false positive rate. Okay? We draw true positive rate versus false positive rate, meaning as the recall is improving, how many mistakes are we making? Right? That's called false positive rate. Total number of false positive, meaning something which was not supposed to be positive is positive, divided by false positive plus true negative, right? So the false positive's behavior is like precision, okay? And when you draw that, this is what you get, okay? So initially, as the false positive rate is increasing, or even if you draw it the other way, the graph is going to be similar. But initially, when the false positive rate is really low, the true positive rate is high, okay, very high. And as you increase false positive rate, the as the false positive rates increases, so so as false positive rate is low, the true positive rate, the recall rate is high in the sense that it's able to recall even if the precision is low. So so sorry, false positive rate, yeah. Even when it in the beginning, when threshold is threshold is a little higher, it's able to recall. And as the threshold is dropping, meaning false positive rate will will keep on as false positive rate keeps on increasing, meaning it's basically predicting wrong outcomes, right? The true positive rate also increases, right? True positive rate also increases. It's like 1 minus the precision. Okay. So recall rate and the true positive as well as false positive both will increase as we go. Ideally, in the best case scenario, this line should have been like this, correct? Even when the threshold is very low, meaning the false positive rate is is right, even in the beginning when the false positive rate is very low, even then the recall should have been 100%, right? Meaning this one should have been ideally like this, and this one also. In the best algorithm, even in the cases where threshold is low, then also the false positive the recall rate is also good, right? Therefore, what we do is this is called ROC curve. Okay, this is called ROC curve. We call it the receiver operating characteristic curve, and it essentially looks like generally like this. If your model is giving this kind of dashed line, right? This kind of dashed line, meaning as the false positive rate is increasing, true positive rate is also increasing, and in the beginning, meaning when it was not classifying many things, the okay, so as it starts classifying more and more things, it also starts making mistakes. So equal number of mistakes and equal number of predictions, right? As the predictions increase, the mistake also increase. And if that's happening equally, right, then we call it purely random classifier, meaning it's just doing a coin toss, it's not doing anything sensible, right? So purely random one have this kind of line. So whatever model you use, they should have at least, at least better than the purely random classifier behavior, right? And how do you decide what is better? By computing this area, by computing this area under the curve. Okay, so what we do in case of what's the utility of ROC curve? By plotting ROC curve, right, we measure this area, how much, what is this area, compare the different algorithms and see which algorithm is giving the best area under the curve. Okay, so that way the recall rate as well as precision both are maximized in case we are picking up the algorithm which has the maximum area under the curve. All right. So higher the recall rate, higher the false positive rate, and the dotted line was up your random classifier. Good classifier stays away from the dotted line towards the upper left corner, right? And a perfect classifier shall have the area under the curve equal to 1. So area under the curve is going to be something like point above zero point 0.5 and between 1 in for most of the models. Okay, so you can generally compute the ROC, the ROC is area under the curve using ROC underscore AUC underscore score using, first of all, you'll have to predict the Y scores the way we said decision function using the decision function earlier, and then we compare it with certain, so this is the scores and this is the actual the values, right? And then we compare the area under the curve, right? We got the area under the curve around 95.9 0.955, which is good, and so on, right? We could also draw it. Um, you could also use the different classifiers, right? So here you can see that here you can see here you can see that this is SGD while this is random forest. Which one will you choose? SGD or random forest? Yes, that's right. So we'll be choosing the random forest. So we are trying to plot the same this kind of graph by ourselves. All right. A question from Robert is that number an aggregate? This number, which number? This one, right? So what is it that we are doing here is we're starting from for different thresholds, correct? As we are in decreasing the threshold, right? What is it doing under the hood is we have the scores here and we have the training data, right? So what it's doing is for each of these scores, it's basically computing for it's taking some value of threshold and computing the based on this and the actual scores. Based on this, it's computing the true positive rate and false at every point of time. Here, at every point of time, it's computing the true positive and false positive rate. How do we do that? By first creating the confusion matrix and then computing true positive and false positive, right? So at every point of time, what it has done is take a threshold, create confusion matrix, compute true positive and false positive, and then decrease the threshold. I think in this case we are decreasing the threshold. So then we decrease the threshold, then we again decrease the threshold, and we keep on doing it till this point of time. So when and why while it's doing it is basically after it has done, it has plotted this area under the curve, and once area of the under the curve has been plotted, then it has computed. So sorry, once the curve is plotted, then the area under the curve will be calculated, right? So the way this curve is drawn is it takes some threshold, really high value of threshold in the beginning, and then keeps on dropping it down, uh, and keep on computing the confusion matrix at every point of time, and compute at every point of time, compute the true positive from confusion matrix, and so on, right? That's what is happening here. So when we say ROC AUC score, so first of all, instead of actual predictions, we have the scores here. Okay. So for different scores, the predictions will be different, and therefore, as the predictions will be different, the it will compute at every point of time as threshold is varying the various metrics such as true positive, false positive, and and so on. Right. That's what is going on here. So as we go ahead, this is what's happening. So this curve, once it's plotted, then we compute the total area under the curve. All right. All right. So far, what we have learned is we learned to do how to do the binary classification. All right. What we did was various steps that we took was we started with dividing the data into training and test. train the binary classifier, choose the appropriate metrics for the task, right? And we understood the precision recall trade-off, and we compared the two models, the various models, using ROC curve. Okay, using ROC curve, the an easiest way to do that is by using ROC AUC curves, right? Because sometimes visually the difference may not be this pronounced. Sometimes the difference could be a little lower. The easiest way is compute the area under the curve and then basically compare the models. All right, so far we have learned about binary classification, right? In case of binary classification, we basically separate the data into two classes, right? We basically predict a column as yes or no, right? So that's binary classification. So we had broken down or converted our problem into 5 not 5 just for the simplicity. And in case, like in our actual problem, we had to predict 1 to 9, and 0 to 9, and so on, right? So that's called multi-class classification. Binary classification distinguish between two classes, while multi-class between more than two classes, right? Now, these multi-class classification or multi-class classifiers are actually made up of binary classification, right? So in binary classification, you can see that it just, if we are able to draw the plane or the line, we are able to classify the two classes, right? So can we use a binary classification for multi-class? Right? So answer is yes, we can use it, and there are two strategies around it. The first strategy is one versus all. Okay, meaning one versus the rest. Okay, say for example, we have to classify the digit image into 10 classes, 0 to 9. One way is to train 10 binary classifications, one for each digit. 0 is the detector, one is the detector, and so. Okay, so we can build, say, 10 such classifier. First one, the way we were saying 5 not 5, we could have 1 not 1, 2 not 2 not 2, 3 not 2, 3 not 3. So we could have such 10 classifiers. Okay, we could have 5 not 5, 2 not 2, 3 not 3, 4 not 4, and 1 not 1, 0 not 0, 6 not 6, 7 not 7, 8 not 8, and not 8, and 9 and not 9, right? If we build 10 classifiers parallelly by manually, even the way we convert our problem into 5 not 5, we create these 10 classifiers, and then once we have created these 10 classifiers, what we can do is we compare the scores. Okay, given an image, we will make it go through all the 10 classifiers and see whose score is highest. Is it 1, 2, 3, 4, 5, 6, or up to 10, 9, right? So then we classify, select the whose score is highest, correct? So that's called one versus all. So we build such classifiers and you can use that. Are you convinced that this strategy will work? All right. The other strategy could be that multi-class classification using OVA, right? So by default, scikit-learn SGD classifier assumes OVA. Okay, so this is how we can just simply use it. We could, by default, almost every algorithms in scikit-learn assume the strategy to be OVA. So under the hood, when we are going to use any of the algorithm like predict, but like SGD classifier or anything, it's under the hood creating 10 classifiers, multiple classifiers. So the way we use this method is we initialize SGD classifier, we train it using fit, and then we predict using predict. Okay, so here under the hood, it is going to check first of all what is there inside Y train. In case Y train is a categorical variable, okay, it's going to create the, it's going to be of course categorical variable, and because we are doing classification, although if it's a regression, it's going to figure out that from that Y-train data set, right? First, it's going to check whether it's regression or it's a classification. And then once it is done, then it'll basically, if it's classification, it'll figure out how many classes are there. Based on that, under the hood, it's going to train those many classifiers and convert the problem under the hood into binary classification. And then once it has trained the 10 classifiers, then it'll use that for predicting. All right. The second one, other than the OVA, okay, it's not yet there. So under the hood, it's doing the same thing. And once it has trained, then it'll pick the class with the highest score, right? So we can do the multi-class classification using OVA, right? And if you want to find out the scores of all the digits, so you can see the digit function on a digit. It'll show you the scores. It'll show you the scores on all 10 scores, right? This is for 101, right? This is 000, this is and so on. So here, this is the maximum score of 101. Okay, so as compared to not one, basically, what is the score of it predicting X, predicting an image, this particular image, some digit as 1, the score is this. What is the score of predicting it as 2? The score is this. Predicting 3 versus not 3. So the score is this. Not 3 is, of course, negative of this. Positive, negative of this will be positive, and 4. So you can see that the score of this is positive, a maximum in case of 5. 5 not 5 is positive. This is positive. This is the highest. So you can see clearly. So under the hood, it's actually training 10 classifiers. A question from Deepak is that from labels also we select training set, Y train. From labels also we select the training set. Okay, could you rephrase the question for me? This question is important. Okay, so what is the slide number? We are right now at 117. So here, whatever is the data we have, this is all the columns from the features. This is the features, and this is only the labels. Okay, so Y train is basically the labels, and that's correct, Deepak. And X train is that. All right, wonderful. So we were talking about this. So under the hood, our normal scikit-learn or almost every library is actually training 10 classifiers, right? The another strategy is we train a binary classifier for every pair of digits. One to distinguish zeros and ones, right? Then second for, let's say, 0 and 2, 0. So 0 versus 1, 0 versus 2, 1 versus 2, and so on, right? We keep on, we compare, we create a classifier that basically distinguishes the two digits every two pair. And so you can see that since there are n such cases, right? So if there are n classes, there will be how many classifiers? N into n minus 1 by 2. For each of the classes will have n minus 1 to compare with, and therefore, so the total pair, total handshakes, the unique handshakes between n people is how much? N into n minus 1 by 2. Question here is that um, in this strategy, we distinguish between whether is 0 or 1. Okay, so we are saying that given a digit, predict whether is 0 or 1, 0 or 2, 0 or 3, and so on. Okay, so we are converting converting it into true false, which is the label is going to be converted into true false. To true means, and they're going to be, say, how many? In this case, how many classifiers are going to be there? Because n is 10, so 45 classifiers, correct? So, in the first case, it'll be like 0 versus 1, which means uh, 0 means true and 1 means false. Okay, that's how it's going to break down the problems and then it'll train it. So in case of MNIST, no, it won't be pair from versus rest. The way we were saying 5 and not 5, we were saying first one is to differentiate 0 and 1s, okay? And another to distinguish 0 and 2, another to distinguish 1 and 2, and so on. In this MNIST case, how many classifiers it will be training under the hood? Anybody? So how many total combinations? Like 1 versus 0 versus 1, 0 versus 2, 0 versus 3, and so on. So how many such classifiers are going to be? Right, they're going to be 45. All right, so 10 into 9 by 2, that's 45, and so on. All right. So doing multi-class classification using OVO classifier, SGD uses OVA by default. Okay, so we need to specifically mention that we are going to use OVO to do OVO classification. So number of estimators are 45 and so on. So hardly anybody uses OVO. Okay, and this is the way we can use. We can just define one versus one classifier, and we are passing the SGD classifier as the argument, and we are saying the max iteration is 20, and then we do the fit, and then we do the predict, and then it'll tell you that how many estimators under the hood were used. Okay, so let's just try this out. The only thing that I am wondering, so basically the OVO is going to be really expensive, right? If you have like 100 classes, they are going to be how many? If their total number of classes is 100, how many will be the estimators under the hood? Around, I think, 455, correct? So what will be the 100 into 99 divided by 2? You can see 4950, these many classifiers. Since as the number of classes are increasing, the complexity, the number of estimators are increasing by square, therefore it's going to be really hard, right? If the number of classes are like, let's say the number of classes are, say, 1,000, then it's going to be in millions, right? It's going to be in millions. All right, so it's 500,000. So basically the OVO is generally too resource intensive and therefore we hardly use it. Good. So let's move ahead and go to our usual notebook. All right, I'm going to run everything above. It's saying that the bad input shape, probably it's asking us to do this. Okay, probably this is asking us. Remember, this is something that we did last time. Yeah. Okay, so all we have to do is, because here it's giving us two things, the y-score as such is having two things. One is the, I think this is the score and this is the prediction. While it wanted, I think, only the scores and only the scores. Therefore, what we did last time was we used this way of picking all rows and only this column, correct? All right, so this way we have, yeah. All right, this is done. Then, okay, we made a mistake here again. I see, same thing. All right, so this is how it looks. So probably this scores function had changed between the scikit-learn's versions. We have recently upgraded all of the lab. So probably that's the reason why we need to probably commit it again. I'll just log in into my account and commit it so that all of you can get access to it. All right. So let me just SSH Sandeep Giri 9034 at e.cloudxlab.com. All right. So here inside the ML folder, we will have the machine learning, right? And this is where we can check git diff classification. This doesn't look very friendly, but you can always find the difference. Okay. All right. So what is it that we're trying to do here? Yes, you'll have to do git pull. Right now I'll do commit and then I'll do push, then you do pull. Okay. Made some modifications for the scores variable. All right. So here we are and okay. So the general way of debugging such problems is to go through my manual and take a look at what they're expecting and learn to debug such issues. Okay, so we already talked about this, and again the same issue. Okay, so saying draw. Okay, again we'll say colon and one. Similarly, colon and one. All right, this seems to be okay. RO. Okay, this I think we had already done or what? Okay, Y train and so on. I think this we had already done. Never mind. So this is where we are, and all right. Again, we'll have to do the same thing. Git commit classification, right? And we'll say messages, some more fixes with respect to the score, right? Score columns. Now, we could also say ampersand ampersand and say git push. This basically chains the two commands together. And if the first one is successful, basically what it does is if the first command is successful, then it runs the second one. Otherwise, it won't. Okay. Whenever in Unix, when some command is successful, it returns 0. And based on that return value, this ampersand operates. Okay, 0 in case of Unix command means it's successful, and otherwise it gives a number. And to find out what number it gave, any previous command, you could use echo question mark. All right. So if I say ls minus l and some random number I'm saying, so there was this, the previous command was not successful, and therefore the return value is 2. Okay. So just to keep you all, you know, on the Unix cell, in case you have not finished the Unix one, please finish that. All right. So the binary classification is what we are discussing, and all right. So here it's going to train 10 classifiers, and then it will give us the result. All right. And all right. In case of one versus one, again, it's going to take the same amount of time, and I see. So here it did actually took a bit of more time because you are using one versus one classifier. One versus one classifier is probably you can find it here. Okay. All right. So it has O(n) square, O number of classes complexity square. However, this the kernel methods that we used to use earlier, there it might be useful. Okay, that's all. Okay, we'll talk about kernel methods again after this, after 2 chapters. So the only thing I'm worried about, I'm questioning here is one thing I'm trying to figure out that how does it do the two classes classification? Because if you see 505, what was it doing is it was the true value. It has only true or false values, right? True represented 5 and false represented not 5, right? When we say 0 versus 1, is it like going to um, create two classifiers under the hood? All right, that's what I'm trying to figure out. Probably I'll do it at some other time. Okay, as notes, I'm going to make my notes here. All right. So how does 0 versus 1 work? All right. Theoretically, it sounds obvious, but I'm still having the question. Okay. So I'll do probably take a look at it again and maybe take a look at their code. So, all right. So we will understand. I think that's what your question was, Deepak, right? Okay. So question from Prasant is it like two classifiers consecutively, like divide it into two and then into two and so on? Okay. So yes, as per the theory, what they're trying to do is they take two classes, A and B, and see if and learn to classify only two things, right? So my question is that the OVA one versus all, right? That has 10 classes, and there are essentially it's doing is uh, it's converting the problem into true and false, right? True and false, correct? And here, when it says that we are creating a classifier 0 versus 1, does it mean true means everything is equal to 0 and false means everything equals 1? Now, there are three states. One, the class could be 0, the class could be 1, and the class could be neither. Then how do you map those true false into 0, 1, and neither, right? That's the thing I'm actually wondering about. So probably we'll take a look at this later. Although when I went through all of this, I was quite clear that okay, one versus one is that, but I'm questioning the strategy because even for 0 versus 1, right? 0 versus 1, it is easy to break it down further into 0 versus not 0 and 1 versus not 1. Or probably there are some algorithms, some classifiers, they which are by default good at separating two classes. For those, the OVO will make more sense, right? All right, never mind. So I'll take a look into it and probably address it more clearly. All right. So multi-class classification is actually extremely simple. Basically, under the hood, it's OVA, one versus all classifier, binary classifiers. And the important part that we want to discuss now is, though there is not much to do here in case of the multi-class classification other than what we studied in the case of binary classification, The next thing we will want to do is we want to do the error analysis. Okay, so we saw that there was area under the curve that was around 9.955 and so on, right? So once the model is identified, it can be improved by analyzing the types of errors it makes. For the previous multi-class classification example of classifying images of digits into digit labels, it can be done by observing confusion matrix and plotting it on the graph, right? So identifying to which label something belongs to is what we are trying to do. So like here, this is all of these are correct predictions. All right. All of these are correct predictions. So, and when we do cross validation here, we have, okay. So what we are doing here is that these are the confusion matrix that we prepared and so on. Right? Now, confusion metrics for larger scale of numbers may not make sense to us. Like, for example, if we try to plot confusion metrics, this is how it looks like, right? So you can see that it is diagonal heavy, you can see, okay? Because the diagonal is basically going back here. Okay, let me describe. So actual was 0, predicted was 0. These many were instances. So 5,000 instances were identified actually at 0, and similarly actually 1 and so on. So this matrix is the cross validation matrix is going to be diagonal heavy. Let's just try to do that in case of the notebook. So this is how it looks like, correct? One thing we could do is here what we could do is we could try to plot it nicely like this, right? We overcome the all of this, we convert it into some color and make this lighter and take a look at that, right? So one thing, okay, this has gone missing here. Okay, one more thing, that's remember our end-to-end project. Okay, in the end-to-end project, what we learned was we should ideally scale our inputs. So there's the part is displayed here that in case you want to improve the accuracy, right, of whatever model we have, we can simply use the scaling and let it run for a while. And so you can see that before the usual way, uh, right? We use cross-val score, we use the SGD classifier, we gave it X train and Y train, and this is our cross validation, number of cross folds in the cross validation. And here the scoring is accuracy right now. Now you can see that the score is this much, right? Score is around 87%. Now, if we just use a standard scaler the way we used earlier, right? And use the scaler to transform our data set and then call crossval, you can see the accuracy has improved. Let's just wait for it. The accuracy should go beyond 90 just by scaling. Okay, so you can see the accuracy has improved by a huge margin, right? At around 4 to 5%. All right. So I mean, when we say 4% here, it's a very big deal. Okay, it's a very big deal because you're improving upon the existing algorithm, and even 1% is dramatically huge. Okay. Now, next part is that we can compute the overall validation. This is where we're preparing all the possible predictions for X and Y, right? Again, we are using the scaled one, and right? So this is how the matrix looks like. Is everybody executing it with me? Feel free to execute it with me. All right. And here, what we are converting this into, we're converting it into the 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 colors. So there is a method called mat show, using which we can display in matplot a matrix. So we give it the confusion matrix and we tell it the color map is gray. Okay. So this is how it looks like. Now you can see that better, that this is whiter and these are darker. Some of these are a little bit more whiter. Okay. And all right. So using the matrix show, you get this kind of matrix. So my question to all of you is, what do you see here? What are the observation do you have? You think of it like a cross-validation matrix, 0 and 0. This is the brightness means those many instances were the true predictions. Okay, actual was 0, predicted was 0. These many. One actual was 1, predicted was 1. There was the clarity was far more. Any other observations? 2 versus 2 means these many numbers, the brightness. So here 0 versus 8, 0 versus 1 was very rare, therefore it's black, and so on. Yes, and you can see the corrective prediction on the mid is low towards high. Yes, that's right. All right. So one is that what we just did was we want to do error analysis in more details, correct? Therefore, this matrix was not making sense. We are pretty good with the images, so we converted the matrix into this kind of plot. Now, here, the right, you can see that this looks fairly okay, just that there are these strips here which you are not able to see, right? And there are these ones that look a little better, right? So you can see these strips, there are these strips, see, and similarly. So those are not clearly visible, first of all, so we'll have to make these visible better. So it looks fairly good since most of the images are all diagonal. 5 looks darker than the others, so this looks really bright, meaning something as 1 has been classified as 1, right? And a point from Prashant is 8 and 9, so some misclassification, that's right. So yes, so 5 looks darker than the other, therefore 5 is being classified as other, right? So 5 looks darker than the other, why? What could be the reason? Question to all. Here the 5 looks darker than the other. Question to you is that there are two choices. Are there fewer 5s in the data set? Could that be the reason? Or the classifier does not perform well on 5s, right? Is it A, B, or both? What is your hypothesis? There could, if let's say you, yes, that's right. It could be both. It could be both until we basically go back and look at the value counts of each label. And until that point of time, if you see this scenario, the chances are both. It could be that in the actual data set itself, there are very few 5s, and or maybe the classifier is not able to detect 5 clearly. It's confusing it with other digits. Okay, so it could be both. All right, keep this in mind. And again, this is a very, very, very important question. So you're given a data set and let's say it's performing great. So what are your hypotheses? That's the common form of questions in case of machine learning interviews or deep learning interviews, right? So In that, do not miss out on the data distribution issues. Okay. All right. Now, if we basically do some kind of normalizing, this whole brightness thing is confusing, right? This whole brightness thing is confusing because it's kind of over, it's not letting us see the others, correct? So what we do is whatever observation we had to make, we made the observation, but to bring them up, bring these spots up, what we have to do is first remove this white, make it black, and then do the normalization, do the scaling of the colors, okay? So that we can compare one less dark with another more dark, okay? So what we are doing here is on the diagonal, we fill the diagonal with 0, right? And then normalize it, normalize it again, okay? This is the normalized score, okay? So So for each row sum, we are dividing it by confusion. Confusion matrix, we are dividing by row sum, and that's how we are scaling. Okay. So here, after we do that, we get this kind of outcome. Okay, let's go back here. Here, first of all, these are the sum of the rows on each y-axis. We are computing the row sums, and then we are dividing the confusion matrix with row sum. That's okay, and then we are filling it the confusion matrix with whatever we have computed here. The diagonals, we are filling it with 0. Okay, and then doing match show. Okay, and row sum is the sum of each row. Okay, contains the sum of all rows. You can just run it and take a look. All right, like this for each of the rows, right? Okay, because there could be both the probabilities, right? There could be more number of digits and so on. Therefore, why we are dividing by rows? So that if, let's say, something's predictions because of because of the that digit being more, right? So therefore the predictions, we are dividing by total number of instances, so that in case, let's say, the data is skewed in the sense that 5 are, let's say, half, more than half, in that case the row sum will be higher, and when we'll divide by the sum of the entire counts, it will basically bring down those values, right? Because number of predictions are going to be higher in case the number of elements are higher. Therefore, because in the cross validation matrix, it essentially it essentially counts the total number of instances. Therefore, we're dividing by total number of instances. In case there's a skewness in our labels, that will be normalized. That's the first thing we are doing here. And then we are filling the diagonal with zeros. And when we do match show, it's going to anyway normalize again and then plot. Okay. So here, I hope it's clear to all. So this was our main confusion matrix, conf mx. We divide it by each instance, meaning each row is divided by the row numbers. Meaning all these values of row are averaged out by dividing by the sum of all. Correct? So we are scaling the each row. Now, then we are marking the whole diagonal 0, and then we are plotting it. Okay, is it clear, everyone? Now this is our image. Okay, this is our image. We could zoom it out. Yes. Now, what are your observations now? This is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9. All right. What are your observations? This is important exercise. This you should be doing with almost every problem. So you can take a look at 0, how it's being predicted. So 0 is being a bit confused with 2 and a little more confused with 6, right? Which actually makes sense. And similarly, the 1 is being confused at 2. This is very strange, right? And 1 is being confused at 8. Similarly, the 2 is being confused with 0. That's right, similar to this one. And 2 is also being confused with a little bit with 1, with 1, right? And 2 is being, all right. Now this one, if you take a look at this, here 3 is being a bit confused with 2, and 3 is being a bit confused, a lot confused with 5. Question from Robert is, one thing I noticed that they are not being predicted evenly. That's right. That's right. So what are your observations, everyone? So I'm just walking you through some of my observations. So no, actually diagonal items we have pushed by ourselves. We have artificially put them 0 because they were confusing us and they were not letting us see the difference between these colors, right? Therefore, we have removed them. If it was perfect prediction, then all of these would have been 0, okay? Because only the diagonal means the correct prediction, right? Only the diagonal means correct prediction. And since we have, what we've done is, this was the earlier, okay? This was how, so this is our cross validation matrix, meaning 0 being predicted as 0, 5,730 times, 0 being predicted as 1, 2 times, 0 being predicted as 2 as 23 times, and so on. Now, looking at numbers, we are not really great at looking at numbers, right? Therefore, what we did was we did a couple of things. One, um, because we know that the if there are certain instances who have unreasonably large numbers, they might look more bright than the other, right? So we divided the entire row, entire every element of row by each of these, the sum of it. Okay, okay. So that is one thing. The other thing we did was we put this here at 0 so that we give a chance for 195 to be compared against 32 and so on, right? So earlier it was like this when we did not put y, though there are these patches here, but they are not visible, right? That's what then we, to improve the visualization, we basically put it 0, and now you can see that those colors, even though they were not pronounced earlier, now we can see them. We can see them clearly now, right? So some of the observations, had it been a perfect prediction, all of these would have been 0, except for the diagonal. Diagonal is something which we have artificially put in as this, right? All right. So 8 and 9 columns, if you see this 9 here is being confused with 7. Actually, for me, it looks like it's 7, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9 is being confused with 8 as well as 7, right? Similarly, 3 and 5 are unreasonably bright. 5 and 8, you can see, 5 and 8 is also bright, and so on. Which makes sense to me that looks like 5 and 3 make sense. They both look similar. 8 and 9 are also. But this 7 thing is not, I'm not very convinced about it. All right, let's go back and try to see. This is 9, right? 9 is being confused as 7 and 8 and 9. All right. So 9 is also being, that's actually correct, right? Sometimes people draw 9 like that. So 9 is being confused with 7 and 7. Like some people draw 9 like this. Some people draw 7 like this. So yeah, because it's not comparing the shapes. It's just comparing the pixels, correct? So most of these algorithms, the way they work is they basically are counting the number of pixels, and if there is a tiny bit of difference in the pixels, it gets magnified, right? So you can see that actually here it should be 9 is being confused with 7 very often, right? Along with 8. So 9 is being confused with 7 and 8, and 5 and 3 are being confused together. And for some reason, the 8 and 1 is still a mystery to me. If you see 1 and 8, and also you can see that if something is being confused here, like 1 and 8, similar relation is here, right? 3 and 5, 3 and 5, correct? All right. Also, 8 is being confused with many numbers. See, many numbers are being predicted as 8. Yes, 1 and 8 is little weird. Perfect. So now 5 and 8, it makes sense that 5 looks a bit like 8, but 1 and 8 is little weird. All right. So one is that gather, how do we overcome it? One is gather more training data for 8 and 9s. Engineer new feature that would help the classifier, like number of loops in the image of the digits and so on. There are these out of the box functions that let you count the number of loop in the graphics libraries. Maybe you could use that to count number of loops. So that way, if you count the number of loops, probably differentiation between 1 and 8 will improve, 8 and 9 will also improve, and so on, right? Now, you could pre-process the images. There are really nice APIs available in Python. One is such as scikit-image, Pillow, or OpenCV, okay? To make certain features stand out more and so on. Now, those are the few things that you could do. Okay. Further, what we could do is we could take a look at, say, 5 and 3 and understand what could be done with 5 and 3. So we could plot things like actually 3 and predicted as 3, right? Then actually 3 but predicted as 5, and actually 5 and predicted as 3, and actually 5 predicted as 5. We could plot such numbers and take a look at those. Okay, let's try that. Let's plot, right? So here you can see that here, oh, where did it go? All right, so you can see here that these are actually 3 but predicted as 3. That's right, this is good. Even this was predicted well, right? Actually 3 but predicted as 5. All right, this actually looks like 5. We can't blame it, but this could have been predicted correctly. Okay, and so on. So a question from Robert is, would PCA work? PCA might improve a bit of performance, but you could give it a try. We'll discuss it again, and remind me that we will try PCA on this. Okay, PCAs are generally great for eliminating certain columns. As you can see that in this case, we have 700 something columns, right? Which is generally too hard for most of the algorithms, okay? Therefore, what we could do is maybe reduce some of the columns. Like most of the images have let's say if we take this tiny image, the corner pixels are useless on all the images, right? Those pixels we could remove using PCA, okay? All right. So our observation is some digits are really badly written, while most are the errors, right? In when we see 3 and 5, they are basically similar. Okay. And since SGD classifier assigns a weight per class to each pixel and calculate the score of that particular class, therefore the 3 and 5, if you look at this, these pixels are equal, right? If you see, this portion is equal, this portion and this portion is equal, and this part of the image is actually, in case of 5, it just shifted to this side, right? So since SGD classifier is just trying to calculate the difference between pixels, and that's why the the difference between 3 and 5 as per SGD is very low, because here this is just shifted to the left. Okay, so that's one of the reasons maybe we can use a better model. So classifier is quite sensitive to image shifting and rotation. So if the image is slightly a little bit shifted, then these classifiers will go haywire, and the that's why they won't perform great on many digits, right? So the other, so what the conclusion is, we should pre-process the image to ensure that they are well centered and not rotated. Okay, so basically the solution here is either use a better algorithm. If you have a better, already you are at the better algorithm, don't worry. Right now what you could do is you could pre-process the image, engineer more features, and try to see that if the problems with rotations are there, or maybe centering the image is there, then you should do that. All right. So even if the shifting of the image in the pixel should not matter much. So you could try removing the empty pixels around. That way, the images will shift, and or maybe just take the image, try to move it to the center. All right. That way, that way you will get a better. Um, all right. That way you will get better results. All right. So I hope this is good. This is what we learned. We divided the data into training and test, and afterwards we improve the model. We try to improve the model using the error analysis. All right. Now the next part is we will learn about multi-label classification. Okay. So a number of problems involve multi-labels. Okay, meaning there are multiple columns on the right hand side. First, we started with single column and single value being yes or no, right? That was the binary classification. Okay. Then we had the multi-class classification, and then now we're talking about multi-label classification. Multi-label classification means there are multiple columns, multiple label columns on the in the Y. Okay, so say for example in this image there could be 3 persons like Bob, Alice, and Charlie, and we could have 3 columns saying that is Bob in there in this image, Alice is there in the image, Charlie is there in the image. So there are 2 classifications in the same image. Okay, all right. So not yeah, there are 2 classifiers. One for predicting whether the individual is there or not. Second is which one is who. Okay, so let's say we could convert our normal problem of MNIST into 2 columns. Instead of predicting actual number on the image, let's say we want to predict 2 columns. That is it large or is it odd, right? Is it large means it could be more than 5, that is 7, 8, or 9, more than 6. Is it odd, meaning is it 1, 3, 5, 7, or 9? So there are 2 classifications in the same image. One classification is predicting the whether it's large or whether it's odd. Okay, so there are two classifications. All right, so step 0 is fetch the data set already done previously, and then we'll train it. We'll also try it on multiple other models. So let's get started with this part. So for now, let's say we are creating this artificial problem whereby we are trying to predict whether a number is large or odd. It could be both. It could be neither, right? So what we could do is simply we start with dividing the data into training and test set, train the classifier using training data set, and then test using some digit. All right, so first of all, what we did was we loaded MNIST, and then we created X and Y, and after that we are creating two Y's. Y train underscore large equals Y train greater than equal to 7, and Y train underscore odd equals Y train percentage 2 equals 1. Right? So now you can see that we have concatenated the two columns, this and that, by column wise. This is a quick way to concatenate it column wise. Now, okay. So, all right, let me restart. So we loaded MNIST. This, I hope everybody is clear. And afterwards, we define two variables, X and Y. X contains data, Y contains target, right? And then what we did was we took the Y, right? We took Y and checked each of the rows against 7. Okay, and this one will contain true or false based on particular row being true or false. Correct. Similarly here also, here I am creating a new column, new you can say array, by dividing by using this formula. Now, what is it doing? Is basically checking if the remainder is 1 or not. If it is 1, it'll be true value, therefore that'll be odd. Correct? So that's how we're doing. Next is we are concatenating large and odd, right, to create a single data frame. I'm completely okay to repeat few things and make it extremely simple so that I would not assume that you have missed anything so far or you remember anything. So that's why I'll try to repeat it often so that not to alienate anybody from the class. Now, moving ahead, so here what we have is we are, say, using this k-neighbors classifier. Yes, Y multi-label has two columns. One is this column and other is that. So here, similar to what we have studied so far, similar to those algorithms, one of the algorithms is k-neighbors classifier. K-neighbors classifier supports multi-label classification. Okay. So we are using that algorithm this time, and we are initializing that algorithm and saying knn underscore clf dot fit, and we are passing this. So here we are training it, and then here we are just predicting something. Okay. So we're passing the same digit called sum digit, which was containing 5, and it's returning correct because 5 is not large, but 5 is odd, right? Now, the performance metrics, let's just take a look at the performance metrics of this one. We'll basically do the cross-val predict, and using that, we are going to say F1 score here, right? So F1 score is here 96.8845, right? So let's take a look at the hands-on. Everybody should open this notebook. All right. So here I'm trying to demonstrate that if you have one vector like 1, 2, other vector like 3, 4, if you want to concatenate them, you can simply use this. So here you can see it's a two-dimensional matrix. Okay. Next is that once that is done, so we concatenated these two and then initialized, and then we are training it. Training is taking some time. Okay, so we have trained it. Now we can do predict. So you can see that we are trying to do cross-spell predict and it's taking some time. Our question is, what is macro here and what is weighted? All right. So there is some way of computing the F1 score. And let me just see. So weighted is essentially the the computing average one. Okay. All right. So here the sample weight. Okay. All right. Yeah. So we can provide the, so this is the average by default. It's binary. This parameter is required for multi-class, multi-label targets. If none, the scores for each classes are returned. Otherwise, this determines the type of averaging performed the data. So calculate the metrics for each label and find their unweighted mean. Unweighted mean. This does not take label imbalance into account. Okay. So here, since this is specifically used for the multi-label classification, and the this one is the weighted in the sense that the particular label, so it calculates the metrics for each label, find their average weighted, find their average weighted by support. Okay, meaning how many are true for each of them, each of the label, and so on. So basically, the weighted one gives more weightages to individual class predictions, and so on. So here we are computing the F1 scores, and there are multiple ways to do that. One is macro, and which is unweighted, right? So in case some of the labels are more in numbers, some of the labels are less in numbers, in that case macro does not do a good job, right? While weighted basically gives the weightages to the right, and it basically finds the average weights by support the number of true instances for each label. Okay, so that is one thing. So all right, I will also need to further dig it. All right. Okay. In case there's a label imbalance, the weighted will make more sense as compared to the macro. All right. That is the quick idea. How much time it's going to take? All right. Let me just see. Okay. So still stuck there. So in such cases, you should generally interrupt the kernel. Let's try again. Is the kernel running? Let's just check the kernel if it's running. Yes, it seems to be running. So Robert is saying that it's working for calculating for 40 minutes. That's not right. Okay, that's not right. It should not be like that. Just go to the control panel and take a look at that. All right. Let me just restart the kernel properly. That'll make more sense. So I'll say cell run all above. Okay. Okay, probably we'll have to kill it again. It's still saying kernel restarting. Yeah, I'll just shut it down for time being. Okay, let's start again. I'll reload it. All right, so this is ready. Go down to the point where we were. All right, so go ahead till this point. Okay, so let's say run all above. Going up, let's take a look. Okay, let's just cancel it. So the asterisk, wherever we notice asterisk, that's where it's going to take time. All right, this is where it's taking time. It's training the random forest. Okay, here it's again doing the training. That's where it's taking some time. All right, going up. So here, this is where it's training the OVO. That one is taking some time. Now moving ahead. Here is doing again some training, and you can see the trainings part are the ones that takes maximum time. All right, Nikita and Robert, did you kill the from here? All right. Now it's doing scaling and then calling the CloudxWell. All right. So looks like we have reached. All right, this is where we are. KNN seems to take some time. All right. Great, great. I'm hoping that this will take some time. All right. Instead of running the first one, I'll just run the second one. Okay. So I'm using the average as weighted. You could use macro as well. All right. All right. It's not finishing. So looks like this CrossWell predict is quite intensive process here because it's going to run the KNN classifier thrice. Therefore, it is supposed to be taking 3 times the time it took. Okay, so I think it took around 2 to 3 minutes or so, and that's why it's taking some amount of time. I think it'll finish now. So I'm the biggest culprit here. All right, so I'm hoping that it should finish. Okay. All right. So multi-level classification is basically this. It's not too big a deal. Just notice that we are using the KNN, K nearest neighbor, right? The K nearest neighbor classification is what we are using here. And it's taking some amount of time, so let's just wait. All right. Do you have any questions before we move ahead? Because we are using CrossWell, the same process might take thrice time. All right, it's not working. Still taking some amount of time. All right, maybe after the class you could give it a shot. It should give you the results. So essentially what we did was we computed the F1 score on our same training data. And okay, so the way it has been computed, the F1 score, it has basically would be computing the confusion matrix. And for confusion matrix, a particular label being classified as something else, right? So since there are multiple labels, those values need to be combined together. Either you could do straight away average, or you could do the weighted average. All right. So macro means straight away sum, and weighted means weighted sum. Okay. Because there are multiple labels and we need to combine them together in order to create the confusion matrix. Right. All right. So the other one is multi-output classification. It is simply a generalization of multi-label classification where each label can be multi-class. So multi-label classification had each column to be a binary, right? Whether the value is true or false, but multi-output classification is where each label can also be multi-class, right? It can have more than two possible values, right? Multi-output classification example is, let's remove the noise from images. We'll build a system that removes the noise from the images. Okay, it'll take, and this is a very interesting example, and we never thought that removing the noise from an image could be a classification problem, right? So it'll take as the input a noisy digit image, and it'll output a clean image. Clean image represented as an array of pixel intensity, just like MNIST. All right, so what we're going to do is we are going to utilize the MNIST dataset, and we're going to produce a pixel. Okay, we're going to produce a list of pixels with their intensities. So in this particular example, this is a very interesting example whereby what we're trying to do is we're trying to train our machine learning model such that given a dirty image, given a noisy image, it should be able to give us clean image. So we are creating this interesting classifier, and here, though it looks like a normal, it looks like a regression problem. It's here being solved like a classification, right? In the output side, there's also an image. The input is also an image. The output is also an image, and which means that if each column is an image, if each column is a pixel, then there are going to be 784 pixels in the output. So 784 pixels in the 784 pixels in the features and 784 pixels in the labels. So this is an example that we are going to run through. So, and each column will have some value between 0 to 225, right? So it has multi-class for each multiple label, right? So there are 784 labels, and for each 74 labels, we have 255 classes. Okay, is the problem statement clear to all? Yes. Only Deepak has replied. Okay, so we are going to basically take an image and clean it. But for that, we need to train the classifier first. Okay. All right, so it's going to have those many images, right? Those many columns now. All right, so first thing we are going to do is the purpose of this system is to be able to, given this input image, given this input image, it should be able to give us this clean image. Okay, that's what we're going to do, right? So what we're going to do here is that first of all, we are going to add the noise. So here, since we don't have much of a training data, what we're going to do is we are going to take clean supervised learning data, add some amount of dirt to it, as in add some pixels to it, random pixels. We'll turn it on and put some intensities randomly, and then we will basically train our models on that. So we take a clean image, add some noise. After adding the noise, that becomes our label, okay? And then we'll train it with that. So we have we are importing random here, and we are generating the noise, then adding this random noise to the X train, right? And here noise underscore test equals rnd dot rand int, right? And here we are basically generating values between 0 to 100 for and these many times. Okay, this is the number of rows, and these are number of columns. So using this function from random package or module, we are able to generate a matrix of this by this, having values between 0 to 100. And we are adding this noise to our X test, right? Okay, so from X, whatever was originally, that is our, okay, so where is that? This is all okay. Now we have noise, we have adding the noise to X test, and we have X train, right? So on the left hand side for the training data set, we have the dirty image, and on the right hand side, we'll have the clean image. Okay, so here we go. We have just used creating this IM show method, using this IM show method that basically takes an image, draws it. All right. So this is after making it dirty, this is how it looks like. And let's go back here. I'm just going to interrupt it. All right. All right, wonderful. So this is what we are trying to do. All right. So here what we have done is we have generated random numbers. Sort of dead on. Okay. I'll just going to kill it. Okay, going back here and seeing whatever imports do I need, and I'll bring those imports. Okay. All right, probably that way we'll be able to just run parts of it. Okay, let me refresh it. All right, so we've just restarted the notebook because it was taking a reasonable amount of time. So now I'm going to just import my rest of the things. Okay, these are the imports. All right. And then I'm going to go down here. All right. All right. This is what we need. All right. Looks like we have to go back. Okay. Never mind. All right. So this also we require. All right. So yes, I think rest will be all okay. Let's go down. So we need random here, and that's okay. X train, Y train we need. All right. So let me walk you through again. So here we generated the noise. This was our original clean image, the clean image. We added some noise to it. Now this is our noisy image. Now this is going to be our X new input, and this is going to be the new output. So noisy and clean, right? Therefore, what we've done is the training modified is this X train, and Y test modify is X test. Okay, or X test modified. This is the test data. Whatever was X, we are adding noise to it. All right. So once that is done, we are plotting a digit, and this is how it looks like. It looks really dirty. All right. And the clean image, the corresponding clean image is here. Okay. So X test mod and Y test mod. Right? Are you clear about what is X test and Y test? So X test is the same image with lots of dirty pixels, and yes, all we did was we took our same image, this image, add some random pixels to it. That's all. As in added some of the values to it. That's all. Right? Now again, we are going to import the KNN, K nearest classifier, and run it. Here the training is going on. Notice that X and Y both contain same size. All right. Question from Robert is that is X and the noise matrix the same size? X and the noise matrix? Yes, that's right. You can see the noise underscore train. This is the dimension that we are passing here. All right. So number of rows in X and these many columns. All right. So here we are first doing the fit and then we are doing the predict. All right. So let me just predict it again. All right. So this way we can build really sophisticated systems even with classification. Okay. All right. I would have thought the image would have been more distorted. Correct. So here the image distortion is not there. We're just putting the pixels on and off at various points. So this image, this clean image has been distorted to this, and that's why it's able to do cleaning really quickly. So after doing the prediction, this is what we are getting. You see this? Here we got the prediction of the same image. If you take a look at this one, let me just try to plot the dirty image. Okay, so let's say this is our plot digit method. We're going to use this. Okay, so this is how it was after prediction. This is how it looks. Okay, and let's take a look at 4001, or let's say 5001. Okay, so you can see that. So it's only these these state away pixels. The problem is simpler here because the noise was added and it was the size of input output are something that we are predicting very well. Imagine that if you have to do the same thing in for audio, for voice, if you have to do the same thing, it'll require a lot of work. Okay, because there the size of noise and size of input would be different from output, and therefore we will need a little bit more work. All right, but it is actually pretty good here. You can see that it really learned how to clean an image. Okay, so it has learned how to even remove these pixels inside 4. All right, and what about this? If I say xtest, so this was original, right? Then we added noise to it. This is how it looks, and this is after plotting. Okay, let's just try to compare the outcome. Okay, so I'll just put it here. So this is after the prediction, and this is the original. So you can see that there is some amount of loss. You can see that, right? There's some amount of loss, but it is not damaged completely. All right. Did it make sense to you, this particular example? All right. So this is a very interesting example. Why? Because imagine that you are asked to do the same thing for lots of data, right? And you don't have dirty data, say, but you know how does generally the dirty data looks like, right? So you can artificially create dirty data and then train your model on that so that it can do neat predictions. All right. So it's a very good example, and it could be used. Similar mechanism could be used for cleaning the audio, cleaning other parts, using the same philosophy. So we used the multi-class, multi multi output multi-output classification in order to produce a clean image. That sounds crazy because producing something sounds like a regression problem, but here it is solved using the classification. All right, so that's pretty much for the chapter classification. We would like to start with the so k and then k and nearest classifier algorithm. We will talk about it, and I'll take it as a question. Okay, let's see if we could. All right, I'll just remove this part from here and then keep this question. All right, so I'll keep this question for later. I'll answer this later when we talk about models. All right. Okay, there's something called nearest neighbor graph. You can take a look at the models and go ahead. All right, wonderful, wonderful. So we learned quite a few things as part of this chapter, and so first we did binary, then we did multi-class, and so on. All right, so that's what we learned about classification. So What we've done is we have learned to solve two kinds of problems. One is the regression, other is the classification. All right. So using these two techniques, basically, you've learned most of the parts of the machine learning. You can start attempting the challenges on Kaggle or anywhere right away. In case you get stuck, just let me know. A very good question from Deepak. Question is, here we are not trying many algorithms for a problem to select one in case of classification. That's right, we did not. We skipped that step. You should try using that step and see if you can improve the performance. You should try hyperparameter tuning. You should also try do the do the sampling in such a way that the images are balanced on both sides. Let's say take the central pixel, and based on that value, create the stratified sampling so that the images are balanced. That's one step that is we skipped. The other step that we skipped was probably hyperparameter tuning and also cross validation across algorithms and so on. Okay, so we should have done that, but we did not do it. All right, ideally, so you try to put those parts into this notebook. Okay, so what we are going to learn now is that how classification problems are very similar to regression in the next chapter. All right, it's very important to know that almost every regression problem can be converted into classification, and that's the reason why almost every algorithm has two avatars. One is for regression and other is for classification. So this is what we have learned about so far. We learned about Python, we learned about NumPy, we learned basics about the matplot and the vector algebra, as in linear algebra. And then we did end-to-end project. We also learned about what is machine learning and so on. And then we learned about classifications. Now is the time to move ahead. All right. In this session, what we're going to do is we are going to learn internals about how models are trained. Okay, so far we learned about practice of solving a machine learning problem, various steps involved, and how do we go about it, right? Now, the one thing that we have been keeping it aside was what exactly happens inside the algorithm, right? So we are going to cover the various algorithms of gradient descent. Most of the supervised machine learning is about gradient descent. So it's important to know the gradient descent and various versions of it. Even when we talk about deep neural network and deep learning, gradient descent is the heart of it. Okay, so gradient descent is the core algorithm, and we would like to walk through it. Okay, so we learn how to control overfitting, right? When something is underfitting, we basically use better models and so on. We make it more complex, and in case something is overfitting, we force it to make it simple by a technique called regularization. So ridge regression, lasso, and elastic net, we will learn how to use each of them and what it means by each of them. All right, so we will continue from here. All right, bye bye, have a good day.